In this lesson, we're going to take a look at several integration techniques that are going to help us evaluate integrals that we may not have been able to approach before. So the first thing we're going to look at, or the first technique we're going to look at, is splitting up a fraction. So let's take a look at this integral. I'm asked to evaluate the integral from 2 to 4 of x plus 2 over x. So in the past, perhaps you would have attempted to use u substitution on this problem. So let's see what happens if we try to do that. So we might try letting u equal x plus 2, in which case du would equal dx. Right, so that would take care of the top of the fraction, and my dx becomes a du. But of course I still have this x in the denominator that I need to do something with. So in the past we've done something that is sometimes called back substitution. We could say that x equals u minus 2, right, if we just rearrange this expression here. And so we'd end up with this integral with some bounds, of course. But we don't know how to solve this one either. Right, so u substitution is not particularly helpful in this case. So let me show you what it looks like to split up a fraction, and we'll see why that can be helpful in a lot of integrals. So splitting up a fraction, anytime you have multiple terms in the numerator, you can split up the fraction. So I can write this as x over x plus 2 over x. And now I will simplify this. This becomes 1 plus 2 over x dx. And now I have an integral that I can evaluate. So I know the antiderivative of 1 is just x, and 2 over x is going to give me plus 2 natural log of the absolute value of x. And then I'm evaluating between 2 and 4. So if I plug in 4, I get 4 plus 2 natural log of 4, and then minus in parentheses 2 plus 2 natural log of 2. So it looks like in the end I've got a 4 minus a 2. So 2 plus 2 ln 4 minus 2 ln 2. And I can simplify this even a little bit more. These coefficients here in front of my natural logs, I can make those exponents. So this becomes then the natural log of 4 squared minus the natural log of 2 squared. So that's the natural log of 16 minus the natural log of 4. And then I can use yet another property of natural logs to combine the subtraction and write this as the natural log of 16 over 4. So this becomes in the end 2 plus the natural log of 4. Okay, so we see here how splitting up the fraction got us to a form that we could easily find the antiderivative of. Let's look at one more example of splitting up a fraction. Here I have the integral of sine of x plus cosine cubed of x all over cosecant x. So you could try using u substitution on this problem. I don't think you'd get very far with it. But let's see what happens if we split up this integral. So I can write this as the integral of sine x over cosecant x plus cosine cubed x over cosecant x. Now I wanted to show you this problem in particular because there's going to be a lot of tricks using trig that we're going to have to use. We're going to need to remember a lot of trig identities. So the first thing we need to remember is that the cosecant is 1 over sine. So cosecant x equals 1 over sine of x. So then what I have, for example, in this first fraction is sine x over 1 over sine x. All right, so what I'm going to do is I'm going to flip this denominator. Flip this denominator here. So then this is going to become sine x times sine x for my first term, and then plus cosine cubed x times sine x, which I can then write as sine squared of x plus sine x cosine cubed x. And we're actually going to think about each of those terms separately because we're going to have to use a different technique to find the antiderivative of each term. So we'll think about the integral of sine squared of x plus the integral of sine x cosine cubed x. So let's start with the integral of sine squared x. How in the world am I going to integrate that? Right? This is sine of x squared, but if I let u equal sine of x, then du would equal cosine x, but there's no cosine in this antiderivative here for me to substitute for. So u substitution doesn't look like it's going to be helpful. Actually, what we're going to want to use here is another trig identity. This is called a half-angle formula. And they come up fairly often in integrals, so it's a good thing to know. So sine squared of x is equal to 1 minus cosine 2x over 2. There is a similar formula for the cosine squared. Okay, these are called half-angle formulas. So what I'm going to do is I'm going to rewrite my first integral using that half-angle formula. So I'm going to rewrite sine squared x as 1 minus cosine 2x all over 2 dx. And then I can pull a factor of 1/2 out front, and I'll simply have the integral of 1 minus cosine 2x dx. And let's go ahead and evaluate that. Of course, the antiderivative of 1 is just x, and here I'm going to get a 1/2 sine of 2x. So now I just need to go back and take care of this other integral. So we have the integral of sine x cosine cubed x. And actually, u substitution is going to work great here. What we can do is we can let u equal the cosine of x. So du would be negative sine of x. Right, and I have a sine of x right here. Okay, so then this is going to become, I need to introduce a negative sign, negative integral of u cubed du, which is just going to give me negative 1/4 u to the 4th plus c. And then, of course, u is cosine x. So it looks like we get then minus 1/4 cosine to the 4th x plus c. So here we had to both split up the fraction and use some trig identities to evaluate the integral. The next technique that we're going to look at, I'm going to call multiplying by 1. And that may sound a little strange, but I'll show you what I mean. So let's take a look at this example here. I've got the integral of 1 over e to the x plus e to the negative x. So you might, first of all, if you were just given this integral without any direction at all, perhaps you would try a u substitution. Okay, so maybe you'd let u equal e to the x. Du then would equal e to the x, so that doesn't look like it's going to work. Maybe we let u equal e to the x plus e to the negative x. Well, then du would be e to the x minus e to the negative x dx. But I certainly don't have that factor anywhere in my integral to substitute for. So it doesn't look like we would get very far with the u substitution, at least not with the ones we've tried. So let me show you a method that will be helpful here. I'm going to multiply top and bottom by the same thing, and that's what I mean when I say multiply by 1. I can multiply the top and bottom of the fraction by the same thing. And in this case, what I am going to do is multiply top and bottom by e to the x. Okay, so let's follow through with that. We'll have an e to the x on top. On the bottom, I will have to distribute. So I'll have e to the x times e to the x, which is e to the 2x power. And then e to the x times e to the negative x is 1. So I end up with this new fraction here. So now that we have a new expression, let's try a u substitution again. So choosing what to make u here is perhaps a little challenging. Let me write this another way. We can also write this as e to the x over e to the x quantity squared plus 1. That would be an equivalent way to write this. So let's see what happens if we let u just equal e to the x. So if we do that, du is going to be e to the x, of course, dx. And that's nice, right, because I see that right here on top. Okay, so let's see what happens if we make our substitution. So my e to the x dx here becomes du. And then on the bottom, I'm going to have u squared plus 1. Now, hopefully you recognize this form. This is a form that we have a basic integration formula for. So let me remind you of that. The integral of 1 over a squared plus x squared equals 1 over a inverse tan of x over a plus c. And here we have this form, right? U is our variable. We have u squared, that's like my x squared, plus 1. Okay, so here a just equals 1, right? 1 squared is 1. So then what am I going to get here? 1 over a, well, that's just 1 over 1, inverse tan of x over a. So here u over 1, and then plus c. And as my last step, I just need to remember to put back in my original variable. So u was e to the x, so this becomes the inverse tan of e to the x plus c as my final answer. So here, multiplying both the top and the bottom by the same expression, which is what we mean by multiplying by 1, allowed us to get to a point where we could use a u substitution to solve the problem. Let's look at one more example where we have to multiply top and bottom by the same thing. So here I'm asked to evaluate the integral from pi over 3 to 2 pi over 3 of 1 over 1 plus cosine theta d theta. Now you can try u substitution in this case, but you're not going to get very far, right? If you take the derivative of cosine theta, you're going to get sine theta, but no sine theta appears in the problem. So we have to try something different of some sort. So what I am going to do here, so I've got 1 over 1 plus cosine theta. I'm going to multiply top and bottom by the same thing, and what I'm going to choose is 1 minus cosine theta. And that might seem kind of a strange choice, but in a second you'll see why. It's going to make things work out really nicely for us. All right, so if we follow through with this, we're going to have a 1 minus cosine theta on the top. And on the bottom, I'm going to have to FOIL. Okay, so my first term is going to give me 1. My outer terms are minus cosine theta plus cosine theta. So those subtract away. And then I'm going to have minus cosine squared theta. So here's another place that knowing trig identities is going to come in really handy. There's a trig identity, a very famous one, that says that sine squared theta plus cosine squared theta equals 1, which of course would imply that sine squared theta was 1 minus cosine squared theta. So if I use that identity, I can rewrite the bottom of my fraction so that I have 1 minus cosine theta over sine squared theta. Now think about where we might want to go from here. Does this look like anything else we've looked at today? This looks like something where it might be helpful to try to break up the fraction, right? Because I have these multiple terms in the numerator over a single term in the denominator, so it's at least something I could try. So let's see if it's helpful in this case. So if I break up this fraction, I'm going to get 1 over sine squared theta minus cosine theta over sine squared theta. Now I'm actually going to rewrite both of these using some trig identities. So recall that 1 over the cosecant, or actually, let me back up and write this a different way. 1 over sine of theta is cosecant of theta. So then using that fact, I can rewrite this first term as the cosecant squared of theta. But what about this second term? Let's look at this out to the side for a second. I could write this as cosine theta over sine theta times 1 over sine theta. Now, cosine theta over sine theta is the cotangent, right? The inverse, or I should say the reciprocal of the tangent. And then we just said 1 over sine of theta was cosecant of theta. So then what I end up with is the integral of cosecant squared theta minus cosecant theta cotangent theta. Now I'm at a point where I can go ahead and take the antiderivative because both of these terms just have basic antiderivative formulas. So the antiderivative of cosecant squared is the cotangent, the negative cotangent. So here I'm just going to get negative cotangent of theta, and then the antiderivative of cosecant theta cotangent theta is negative cosecant theta. So minus a negative is going to give me a positive cosecant theta. And then I'm evaluating from pi over 3 to 2 pi over 3. So I just finished by plugging in these bounds. So negative cotangent of 2 pi over 3 plus cosecant of 2 pi over 3 minus the quantity negative cotangent of pi over 3 minus cosecant of pi over 3. That is plus cosecant of pi over 3. And we'll stop here for this problem. So to review, what we did here is we multiplied top and bottom by the same expression. And then from there, we used a series of trig identities to rewrite this in a way that we could take the antiderivative of. Let's take a look at another technique that can be useful in integration. So what I have here is I have the integral of x squared plus 3x minus 2 over x plus 7. So what might you try in this case? Well, perhaps you would try u substitution. Maybe you'd let u equal this quadratic, x squared plus 3x minus 2, in which case du would be 2x plus 3 dx. But that doesn't really look promising. I have this x plus 7 in the bottom, but I never want my du to be in the denominator, so that's not going to work. And if I were to let u equal x plus 7, that wouldn't get me anywhere. So it looks like I need some other approach. And the approach that we're going to use here is actually what we would call long division. So I'm actually going to do long division on x squared plus 3x minus 2 divided by x plus 7, and that will allow me to rewrite this rational function. And maybe then I can evaluate the integral. So it's probably been a while since you've seen long division like this. So let's work through this. So I'm taking x squared plus 3x minus 2 and I'm dividing it by x plus 7. So how does this work? Well, what I'm going to do is I'm going to look at this x here and this x squared, and I'm going to ask myself, how many times does x go into x squared? Or another way to think about it is x times what equals x squared? So the answer to that question is x. So I'm going to put an x right up here. Then my next step is I'm going to take what I just wrote up here, x in this case, and I'm going to multiply it by x plus 7. So x times x plus 7 is going to give me x squared plus 7x, and then I'm going to subtract that quantity down below here. Okay, so x squared minus x squared is just 0. And then I've got 3x minus 7x, so that gives me negative 4x, and then I can bring down this minus 2. And then I do the same thing again, but now I'm looking and asking myself, I'm still looking at this x out here, and I'm asking myself, how many times does x go into negative 4x? Well, that's going to be negative 4, so I put my negative 4 up here, and then I take negative 4 and multiply by x plus 7. Which is going to give me negative 4x minus 28, and I subtract that whole quantity. So negative 4x minus negative 4x is 0, so those cancel. And then I have negative 2 minus negative 28, which gives me positive 26. And now I'm finished because x will not go into 26. Okay, so what just happened is I divided these polynomials, and the result was x minus 4 with a remainder of 26. And the way I write my remainder is plus 26 over x plus 7. So now I can rewrite my integral using this result. So I can say that my integral from before is equal to the integral of x minus 4 plus 26 over x plus 7. And that is something that I can evaluate pretty straightforwardly. So the antiderivative of x, of course, is just 1/2 x squared. And then I have a minus 4x. Plus, I have a constant of 26, and then the antiderivative of 1 over x plus 7 is going to be the natural log of the absolute value of x plus 7. plus c. So this is my result in this case. So once again, what we did here is we used long division to rewrite this rational function. Now long division is going to work when the degree of the numerator is greater than the degree of the denominator. Or also when the degree of the numerator and denominator are equal. Long division would also work in that case. Let's take a look at one last technique together. So here I've got the integral of 1 over x squared minus 6x plus 13 dx. So what's going to happen here? Well, I could let u equal the denominator, but then du would be 2x minus 6 dx, but there's no other x's to substitute for in the problem. Long division isn't going to work. I don't have a polynomial in the numerator, so it looks like I need some other approach in this case. And what we're actually going to do is we are going to complete the square in the denominator. So it's probably been a while since you've completed a square, but this is a really, really useful skill. So completing the square is just a way to rewrite a quadratic. Okay, so this is how it's going to work. I've got x squared plus 6x plus, and I'm going to add something here. Some special magical number that's going to make this all work out really nicely. But so that I don't change the expression, I'm going to have to end up subtracting that number as well. Okay, so let me tell you how to find that special magical number. So what you're going to do is you're going to look at the coefficient of the x, of the linear term, which in this case is 6. Technically it's negative 6, although the sign isn't going to really matter in this case. So I'm going to take that negative 6 and divide it by 2, and then square that. Okay, so just take that coefficient, divide by 2, and square it. So in this case, that is going to give me negative 3 squared, which is 9. And 9 is my special number. So I'm going to add 9 here. And I'm going to subtract 9 as well, so that technically I don't change the expression. Okay, so then what I have is I have x squared minus 6x plus 9, and I'm going to group those terms together. And then I have this plus 13 minus 9, which is just plus 4. We'll put that out to the side for now. So why is 9 so special? Well, this expression here, this x squared minus 6x plus 9, if we did our work correctly, this should now be what we call a perfect square. It should be able to be factored as a perfect square. And if you check, this actually factors into x minus 3 times x minus 3. So then this becomes x minus 3 quantity squared plus 4. Okay, so that's why this is called completing the square. All right, now we've got this binomial that's squared. So I'm going to rewrite my integral then using what we just discovered. This is now 1 over x minus 3 quantity squared plus 4 dx. Well, hopefully you recognize that form. This is a basic antiderivative form that we should know. To remind you of that one more time, the integral of 1 over x squared plus a squared dx is 1 over a inverse tangent of x over a plus c. And that's the form we have here. Right? We have something squared, a variable expression squared, plus a number squared. So let's just do a little u substitution here, just to make it match this form more exactly. We'll let u equal x minus 3. So then du just equals dx. So I've got the integral of 1 over u squared plus, and I'm going to write this as 2 squared. Okay, so if I take that antiderivative, I'm going to get 1 over 2 inverse tangent of u over 2 plus c. And then, of course, I want to put back in my u, so this becomes 1/2 inverse tangent of x minus 3 over 2 plus c. All right, so in this case, completing the square, put this in a form that we knew how to take the antiderivative of.